Let me first apologize for the sort of subtitle here, where I did say that I mean the original plan was to discuss Coulomb gas and collective field theory, but what I realized is maybe it won't be exactly possible to cover everything. So today our main focus will be, so from last time what we saw was we sort of got a qualitative picture of how we expect large and matrix integral to behave, and the central highlight that I sort of discussed last time was to start off with a very simple looking field theory in zero dimension, where the dynamics was governed by a bunch of Hermitian matrices, which and these Hermitian matrices were basically constructed, and in fact their elements were chosen randomly from a Gaussian distribution. And this is what how the path integral was defined, and the object that you see here, S of m, as of now it's just a simple polynomial. We don't have absolutely any sort of background on which these matrices depend. So as of now there is no time, there is no space. These are purely simple looking invariant polynomial. By invariance I mean things that are nice under unitaries. So of course, because you have things like trace, when you conjugate with a unitary, so if m goes to u dagger mu, things are invariant. And as we will see today, that this particular conjugation actually plays a huge role. What we did after that was we carefully defined the propagators of this theory and worked out some sample expectation values. And what was extremely crucial, and which I wanted to highlight repeatedly last time, and I would like to highlight again, is the fact that for such matrix model, the index structure of the propagator is extremely important. So here you can see when I have mij mkl, I have a 2-point propagator. The first talks to the fourth, so I talks to L, and J talks to K, that is the second talks to the third. Then we moved on to diagrammatics. We constructed Feynman diagrams, and what we basically saw was that in the large n limit, what contributed was planar diagrams. And once we take the 't Hooft limit, so 't Hooft limit is this very special sort of place within your parameter space of your theory, where you tune your couplings in a way such that n is large, gs is small. So the 't Hooft limit is something that is going to come back today again. That's why I have not written it out explicitly, but the central point was this coupling gs is large, but n is, so gs is small, but n is large, such that their product is constant. And that coupling precisely is lambda here. And what we saw was, if we write down this particular partition function, we can interpret this partition function as a sum over certain over some over genus, basically Riemann surfaces over various genus. And turns out that this is precisely exactly what also happens for oriented closed bosonic strings. And basically this essentially we were doing a sort of non-critical string theory in disguise. So that was the central upshot. So I promised that I will give a bunch of references, and so this is actually a very partial list. So this is what the first couple of lectures are based on. I must mention, so the first book, of course, amongst reviews, I'm going to get the archive numbers and what I'm going to do is I'm going to send off these slides, the slides of last week as well as this week, after I finish off writing out this particular slide, where I'm going to mention the archive numbers and details of at least 4 or 5 more review articles, which are more recent. So firstly, the book of M.L. Mehta is sort of like the Bible on random matrices, which is kind of like, I mean, it's currently, I think, in its 7th edition or something. Although the book was written in 1979, it's equally relevant today. The second one is somewhat more recent take. This was probably written 3 or 4 years ago. The thing about Mark Potter's and Bouchard's book is the fact that, so both of them are actually physicists who has now moved into finance. And their book is very nicely partitioned into 3 parts, one for mathematician, one for physicist, and for people who would like to go into the financial market. And this has a lot of like problems which involves numerics. So our main sort of motivation would be, because since we are more interested in understanding gauge theory, It will be Marino's book on matrix models and topological strings. By the way, all of them, the titles of all of them involve random matrices or matrix models and things like that. But I'm going to fill out these things explicitly and send off the full list of references. Okay, so again, to highlight what we saw last week was we computed this path integral over eigenvalues. And our starting point was this very simple model where this S of m was a polynomial. And this is precisely how we define the measure on which the space of matrices on which we are integrating. There were n many real quantities, which is precisely what contributes to the diagonal elements of the Hermitian matrix M. There were n into n minus 1 by 2 real quantities and n into n minus 1 by 2 imaginary quantities coming from the non-diagonal sectors. And this was sort of a very brute force way. And we, even within this brute force way, we computed the propagators and things. And we, in fact, got quite a lot of mileage, and we saw that we can actually perform a genus expansion and map it to something like non-critical strings. Now, what it naively sort of is suggestive of the fact is that so we have a bunch of Hermitian matrices, and what we know from our very basic linear algebra is I can always use a unitary to diagonalize a Hermitian matrix. So it might be easier and more practical provided I have this measure as a product over these eigenvalues instead of these raw matrix entries that or the raw matrix entries from the ensemble that we start with. So the central question that we right now want to answer is, how does this matrix integral look like when we express it as an integral over eigenvalues? Now, when we try to diagonalize any Hermitian matrix with a unitary, so you have this u lambda u dagger, and these lambdas are of course diagonal. What happens is it determines this lambda only up to a phase. And that actually brings in a nice structure to it. And that's what makes things non-trivial. So suppose for a moment, consider a matrix which belongs to the so-called group u1 to the power n. By u1 to the power n, it simply means you have a diagonal element where all these element entries are basically elements of u1. So it's of the form e to the power I theta. What you will notice is that both this matrix U as well as UV both end up diagonalizing this matrix M. And this you can see very easily by simply taking this sort of conjugation with the diagonal matrix. And V lambda V dagger is in fact equal to lambda because V is also diagonal, so is lambda. So they simply commute. And V dagger V is 1. So in essence, what is happening is basically the phase factors are cancelling out each other. So the physically distinct diagonalizations basically form an equivalence class. So if I start with a U and if I have multiplied with some other matrix which is of this form, which is an element of U1 to the power n, I'm basically going to consider them to be same. So at the end of the day, the space of inequivalent choices that I have in the eigenvectors is basically this coset, which is Un quotiented out with U1 to the power n. I'm effectively throwing out elements of this form. That's basically what this means. And this group UN gets divided into equivalence classes, and these two unitaries effectively are equivalent if they differ by a right multiplication or by a left multiplication by this matrix in U1 to the power n. Here, actually, left and right multiplication is not going to matter. Now, as I was saying, now that we have identified that there is this ambiguity and we have to effectively work with elements belonging to a coset like this, what we would like to have, and now that we know that we are performing this transformation, of course, this will bring in a Jacobian. So ultimately, the main hero of today's story would be how this measure transforms. Now, this is our eventual goal. So to put it very simply, we have the original variables Mij. And now what we want to do is we want to go to this new set of variables where at least n of them are this set of eigenvalues. Now the space of n cross n Hermitian matrix, it's a real vector space of dimension n square, of course. We saw because there are n diagonal elements and n into n minus 1 by 2 real and imaginary part. And they are isomorphic to Rn square coordinates. Now, just for a moment, imagine, so our main point is basically what you see in the title of this slide. what we would like to do is, given this space of Hermitian matrices, I would like to define a metric on it. So why do we want a metric? So it is precisely because there is an isomorphism between n cross n Hermitian matrix and real n square coordinates. The most naive guess that you can think of assigning a metric to two Hermitian matrices M and M plus Dm, which are sort of close by, is this kind of a natural metric. It's simply you take the difference in each of the matrix element, you take a mod and square them. Also, as it happens, you can see that you can always write it in a trace form. Now, this immediately is suggestive of something. What this tells you is that this is manifestly, because you see, because the fact that you can write it in a trace form, it is manifestly invariant under unitary conjugation. So you do a transformation like this, and effectively this object is going to be invariant. So the main motivation of defining this metric is the following. If I give you a bunch of coordinates which are Euclidean in flat space-time, you do a transformation, then at the end of the day, the Jacobian will be captured by the new metric, by the square root of the determinant of the new metric. And that's what we are after. Okay, now that we have started from this, we have done this conjugation, and U is a unitary. Taking a derivative gives me this kind of a form of M, where these three terms are effectively coming from applying the derivative operator via Leibniz rule. You simply apply product rule. Now, at this point, define this particular object A, which is U dagger du, which is anti-Hermitian. The moment you see A U dagger du to be Hermitian, you can immediately declare that A has to be of this form, where you have I multiplied by something Hermitian. Now, in this coset that we just spoke about, where there was this ambiguity, within this coset, because like A is an anti-Hermitian matrix, the diagonal elements of script L, so this has to vanish. Now, so L is Hermitian, but with a special kind of Hermitian. So remember, we are after this metric, which is this trace invariant form dm dagger. Now things are conventional, like computationally, it becomes convenient. Of course, you can directly take this M and dm dagger and then plug it here and compute. But it becomes actually convenient if you do a further conjugation by the unitary, because if you don't, basically you will end up with things like trace of du something du, and you will get things du square. However, if you go via this path, then things are computationally more easier. And a very straightforward computation where all you need is cyclicity of trace and the symmetries of mu and a. By symmetries, I simply mean to say that whether these matrices are Hermitian or unitary. So you're simply going to use things like m dagger equal to m, u dagger u equal to identity, and a dagger equal to minus a. Once you do that, the final expression that you obtain is here. Now, so by the way, is my cursor visible? Hello?
Yes.
So this is what you obtain. Now, focus on the third term. So remember that d lambda, this is always diagonal. And because all my diagonal elements of dl was identically 0, this object is always non-diagonal, which basically means if I take a trace multiplying these two objects, it's always going to vanish. The first term, however, it's very simple. It's simply nothing but the square of the eigenvalues, the square of the differential of the eigenvalues. The second term can be simplified. And finally, because there is a trace, so there is a sum over ij times ji, and there is a sum of, of course. So by the way, for the purposes of this talk, there is a lot of times when you will see objects like this. Observe here, there are two indices, j and I. Although I am going to write one sum and simply denote I not equal to j, secretly this involves two summations, one summing over I, one summing over j. This is very important, as we will see later. This is going to play a very important role when we are discussing equations of motion at large n of these kind of matrix models. Okay, so after a very short simplification and noting the fact that L is Hermitian, you finally end up with the second term of this form. So, putting all the ingredients that we have obtained till now, this effective distance, this notion of distance that we define between two nearby Hermitian matrices, basically becomes this. So now what we did was we started off with a bunch of Hermitian matrices M. We did a transformation which took it to its diagonal elements, which were like its eigenvalues, and some off diagonal elements, which I've called curly Lij. And naturally, because we have done this transformation, it will affect the matrix integral dm via the Jacobian. And the Jacobian of this transformation is nothing but the square root of the determinant. Now look what the metric is. Along the eigenvalue direction, it's simply 1 for every d lambda I component, and for every d li, it's this gij. So I mean, this is for each of the two real components, one coming from real part, another coming from imaginary part. So yeah. So when you compute the square root of it, and this is why when you compute the square root, there is actually a factor of this object whole square, because half of it comes from the real part, half of it comes from the imaginary part. When you take a square root of it, you end up with 2 times lambda I minus lambda j square. And this is a factor, numerical factor, that people keep for convenience in matrix integrals. It does not really play a major role in terms of physics. But of course, it's good to keep because it's good for normalizing your density functions and so on and so forth later. So the final answer that we get for the integration measure dm, as now a measure and taken over eigenvalues, is something like this. Now notice there are a couple of things. This curious factor that appears here, mod lambda I minus lambda j product over all I not equal to j. Of course, I is not equal to j because otherwise this thing vanishes. Then there is also this other part that came from the non-diagonal elements, this dl. There is also so the point of this long song and dance was to get to this expression. So now this is what we started off with. We wanted to express our measure as a product over eigenvalues of the matrices, and that is what we have done. But along with that, we have obtained something extras. Now we are going to talk about this extra stuff. So the first thing to note here is this volume of Sn. So you see, when you write down the eigenvalues of M after diagonalizing in this matrix capital lambda, of course, one thing that you can do is you can permute among those eigenvalues. So you need to divide by that extra volume. And that's just simply n factorial. It's just a fancy way of saying that this is the volume of the permutation group Sn. It's just n factorial. Number of ways I can permute the n eigenvalues. This object here in brackets d curly L, this is precisely what represents the volume of this coset space un modded out with u1 to the power n, which is what we spoke about. This is precisely that ambiguity. Along with that, we have encountered this very interesting object, which I'm going to call capital delta. And this has a name. This is known as the Vandermonde determinant. And this Vandermonde determinant plays an extremely crucial role. So it is essentially the determinant of this particular matrix. This is known as the Vandermonde matrix. It looks very nice in structure. It simply has, along the rows, it just contains higher and higher powers of the eigenvalues all the way up to n minus 1. Okay. So far so good. The question is, now that we have obtained this very strange factor for free, what does it really imply? So what we saw is, if we started off with a very generic matrix model, which is zero dimensional. So at this point, I have not specified whether W of M is strictly quadratic or not. It can be anything, any nice invariant polynomial. And by the way, when I say nice invariant polynomial, always at the back of your mind, you should always think, I only mean things that behave nicely under unitary conjugation. So typically these objects involve things like traces, and they are typically powers, simple powers of these Hermitian matrices. So now that we have written this, we got this particular factor. One was this n factorial factor coming from permutations of the eigenvalues. And along with that, there was this definition, like we diagonalized the eigenvalues only up to a phase factor. And that volume is contained within un coset u1 to the power n. Now, the reason for harping on the fact that these WMs are these nice polynomials which are independent of anything else, and they other than the eigenvalues themselves, and they are independent particularly uh, of any unitary transformation, effectively is the statement that this object that you saw, this dl, so whenever I write e to the power wm, these w's do not depend on this curly l. That is effectively what this means. So that's why we can take it out of this integral, and that's why you see this volume has now appeared in front. So whatever w you think of, you can think of trace m to the power k, or so trace of m to the power k is simply going to be lambda 1 to the power k plus lambda 2 to the power k, and so on and so forth. All of these things you can write purely as polynomials of the eigenvalues of the matrix M. You do not need any information from the non-diagonal part. And that's what is meant by sort of modding out with this invariant non-diagonal volume. Now, a very natural thing to do would be, so the other curious thing that we got was this Vandermonde factor. So the most natural thing to do would be to define an effective theory in terms of this Vandermonde factor. So what you do is you simply take this, you raise it as to an exponential and define an effective theory. The moment you try to define an effective theory, so all you have to do is simply write this expression, plug in the expression of delta, write it in this form. This effective theory looks somewhat like this. Now, there are a couple of interesting things. Number one, of course, which I just discussed. One is that WM. Of course, we have because WM is nice and it's an invariant polynomial. It depends only on the eigenvalues lambda I, and not on these angular variables. So doing this process where I stick only to observables which depend strictly on my eigenvalues has a fancy name. It's called sticking to the singlet sector. The change of coordinates has given rise to this non-trivial Jacobian. And what this effectively does is it sort of tries to compete with the original integrand, which was given to me as a potential. So W was the original given potential. And notice it comes with a negative sign in front. And these two terms sort of tries to compete, and you can easily see as lambda j tries to approach lambda I, this object sort of blows up. This object starts dominating and making the effective action more and more larger in magnitude. So in a sense, there is an effective repulsive pressure against eigenvalues coming very close to each other. Of course, they can be close to each other and they will lie within a particular interval, but they can't be very close to each other. So this is exactly the level repulsion that I was discussing, which Wigner saw in very general random matrix theories. So this is precisely the reason why you see level repulsion. This is the origin of the level repulsion. So by the way, also for other matrix model, which are not Hermitian, like if you choose a Gaussian orthogonal ensemble, or if you choose a Gaussian symplectic ensemble, what is going to change is this factor that you see. So here, in case of Gaussian unitary ensemble, since we are dealing with a bunch of Hermitian matrices, what we saw is it's basically the square of the difference of the eigenvalues. For orthogonal, you are going to get this power 2 to be linear, and for symplectic, this power is going to be 4. So 1, 2, and 4 are precisely known as the Dyson index. So these are the things that are associated with the three different kind of ensembles that we have. And depending on that, which ensemble you are in, this factor is going to change. So the factor 2 is for unitary ensembles. For orthogonal, this would have been 1, and for symplectic, this would have been 4. But the central upshot is that the signature of level repulsion is going to be there uniformly. It does not matter which kind of ensemble you are working with. Okay. Now let us look at the saddle point approximation at large n. So now that we have got a effective action and we have defined something like this, our central aim,
Uh,
sure. Is there a
so,
question?
can we think can I think the Vandermonde determinant as like the major Jacobian?
Yeah. That is exactly what it is. That is exactly what it is. So if you see here, uh, I mean, this is precisely what I mentioned here. What we did was we started with a simple Euclidean coordinates, a bunch of Euclidean coordinates, right? Which was Mij, n square Euclidean coordinates. This is what we started off with. Then we did a transformation. M is u dagger lambda u, u lambda u dagger. Now what I want to find is, because now I have this sort of a metric, I have defined a metric in the space of Hermitian matrices. The Jacobian is nothing but it's the square root of this determinant of this metric. And that is what it is. Is that fine?
Yes, yes.
Yeah. So the Jacobian of this transformation is simply the square root of the determinant of this metric. That's what is goes at this point. And this is how you compute it. By the way, please feel free to stop me at any point of time if you think I'm going over anything very fast, or if I should pick up more speed, or I should slow down, anything. Yeah. Okay. So we, as of now, have discussed what are the implications of this Vandermonde factor. So now let us begin a large N analysis. So our central aim is, so after expressing everything and fixing ourselves to the singlet sector, we obtain this effective action, which is in the first blue colored box. Now recall from last session, what we saw was there was this very nice limit within our parameter space, which was the 't Hooft limit that I spoke about, where we essentially saw planar diagrams dominate my vacuum to vacuum amplitude. And the 't Hooft coupling was defined in a way where n goes to infinity, gs, the string coupling was small, such that t is fixed. So a small notational departure from the last session was because we were not working with eigenvalue basis. The 't Hooft coupling I defined as lambda, which is what is also conventionally done in high energy literature. But since this time I am dealing with eigenvalue basis and the eigenvalues are lambda, so to avoid any kind of confusion, I'm calling the 't Hooft coupling as T. Okay, so the effective action now, because I have taken this kind of 't Hooft limit, so in the first term, you see this denominator 1 gs times n gets replaced with t, and I'm left with a factor of 1 by n. However, there is no gs piece that came into the Jacobian. The gs piece was strictly something that was present within the potential. So effectively, at the end, we have this. So in the larger limit. Now, notice something. So this is what I'm going to call the leading piece, simply the sum over the potential. Also, again, to reiterate, because we are in the singlet sector now, this potential that you see now depends exclusively on the lambda i's. The potential is such that there is no dependence on the Lij's that we saw. Now, the sum over the n eigenvalues in the first term is roughly of order n. So that makes this overall action some order 1 quantity. Because remember, this t is right now a fixed number. This is something finite. It's not because we are in this strange limit. It's not of order n. Now, this object that you see going as 2 by n square, it's the second piece. And because now n is large, you can think of this as some kind of a h-cut parameter, the Planck's constant that we usually do. So in a sense, the second term can be thought of as a kind of quantum correction due to this change of basis. And n going to infinity now will correspond precisely to a semi-classical approximation. Or in other words, the dominant contribution to the path integral, the quantity z that we define, has to come from the saddle point configuration that is going to extremize this effective action. Okay. Now, this is the point where we are going to take a very, very sharp departure from all sorts of conventional field theories that many of you might have encountered before. So, to reiterate, this is what the effective action was. Now, if you vary this S effective with respect to the eigenvalue, you are going to end up with this kind of an equation. So as of now, okay, I should be a bit more pedantic about my discussions. So as of now, what you see, I have not yet taken a large n limit. The only large n fact that I am using is this fact that I am trying to think of this term as sort of a quantum correction to this leading piece. Otherwise, operationally speaking, all that I have done is I have simply renamed this coupling GS times n as T. Okay. So now, so we were working with a bunch of n cross n matrices. In the finite n limit, I have n many equations. And notice something. The equation of motion of these eigenvalues now actually involves a sum. There are n many equations that I have, and each of these equations actually involve a sum. Each equation corresponding to each eigenvalue. Now, the eigenvalue distribution at finite n can be defined by something like this. So this would be the most general naive definition of a density function that you can think of. It sort of means that every time, so you are sort of scanning over the interval where you can possibly find your eigenvalues, and every time you hit an eigenvalue, you sort of have a counter that clicks. That's what precisely this delta function does. Now, it is not very unreasonable to expect that at large n that this object rho of lambda will become continuous and will be non-zero over a finite interval, which basically means that rho lambda has what is known as a compact support, and it will vanish outside this finite interval, which I'm going to call curly C. This particular form, or rather assumption or ansatz of solution, is known as the one-cut solution. Now, to reiterate, we got this equation of motion. From there, we obtained this particular equation of motion for finite n, which was as of now, yet everything is discrete. Physically, what is happening? Physically, what is happening is something like this. So, assume that this potential that is there, W, it has a single minima. Suppose the minima is at the point x naught. If you think of the eigenvalues, these lambda 1, lambda 2 up to lambda n as coordinates of n classical particles on the real line, then effectively this equation of motion that you see on the right hand side in the top colored blue box, it is as if those particles are subjected to an effective potential like this, which I am calling W effective. If I give you n classical particles subjected to this potential and ask you to calculate equation of motion, you would give me this exact same answer. Now look at what happens here in the potential. The log piece here, this is precisely like the Coulombic repulsion between the eigenvalues. And so when this 't Hooft parameter T is very small, what happens is that the first term, the potential term that was given within our theory, this dominates and all the particles sort of bunch up at x equal to x naught, and which is precisely where the first derivative of W vanishes. And at t equal to 0, this entire interval over which these bunch of eigenvalues are distributed, it sort of collapses. And as t increases, this Coulombic repulsion between these eigenvalues increases, and they sort of try to push apart. And then they spread out over some finite range of interval C. So this is the kind of picture we will always have in mind when we set up problems like this. Now, for any function of this eigenvalue f of lambda, it is very easy to write down a continuum version. And if you have a discrete sum like this, then the continuum version is simply the integral of f weighted with the density function. And you can very easily see, this is how we defined our density function. If you simply take this rho of lambda, plug this within this integral, and actually perform the integral, every delta function is going to click when lambda is equal to lambda I, and you are effectively going to get back this discrete sum. Now, If I naively use this, what we get is in the continuum large n limit, the equation of motion of these eigenvalues looks like this particular integral equation. And this is where you see a very, very, very sharp departure from usual field theory that one might see in standard textbook. You do not expect your equations of motion to be integral equations. Generally, when we talk about equations of motion, we typically write down a Euler-Lagrange equation and things like that, which are typically differential equations. However, and this is what I was trying to point out before also, when we wrote down this S effective, so this one had one single summation, I going from 1 to n. When I wrote down this summation, I less than j, look, there are two indices here. Secretly, there are actually two summations. So one of the summation drops off, and you are still left with another summation which becomes integral in the continuum limit. And that is precisely why now your equation of motion looks something very, very non-trivial. So it's an integral equation. So now that we have got this integral equation, um, which is not a differential equation.
Just a naive question.
Yes.
How do you derive the equation of motion in this case? The same variation principle, or
Yes, you can do it. So one is like, you can just see 1 by n sum over 1 by lambda I minus lambda j. Lambda I minus lambda j is precisely this f.
okay.
So you replace f with integral f of rho lambda and you get this. This is one way. The second way is you can directly go to the continuum limit in S effective itself. In which case you will get a single integral in the first term and you will get a double integral, but with a cut. So you have to do a careful thing because I cannot be equal to j. So you have to be a bit careful here, and you can also write it. I think I have the expression of S effective in the continuum limit later. And all you have to do is you do the same thing. You take a variation with respect to lambda, or because when you go to the continuum limit, lambda will be replaced with rho of lambda. So you take a variation with respect to rho, and you will get, using simple variational principle, you will end up with this equation. So in a sense, it's still using the principle of variation, but not in a standard in the usual Euler-Lagrange way, because there is an extra integral now. That's all.
Yes, but we have to take some continuum limit to apply the variation principle, right?
I mean, here, for example, if you look at the equation of motion here, all you would do, like, you can write down an equation of motion even in the discrete case. This is the equation of motion in the discrete case, right?
Okay, considering lambdas as parameters. Okay.
Yeah. I have a bunch of, like, I can write down a lattice. I mean, this is basically a lattice theory, right? So my lambdas are my dynamical parameters, and all I have done is simply demanded that del S effective del lambda I has to vanish. That's all I'm demanding. And that gives me this equation of motion. Because I mean, I don't have anything like a lambda dot. There is no time or etc. or anything. So it's the most trivial thing that you can write down. Yeah.
And in the right hand side, like the equation of motion you have written, in that equation of motion, if I plug back the density equation rho lambda equal to that 1 by n, then only I can get the last equation, right?
Yes, of course. If you just simply take this rho lambda equal to, if you take the discrete sum and if you plug it
And
back
then
here,
I say that n
you
goes to infinity, so the discrete sum will be replaced by the
yes.
integral.
So you had a bunch of discrete sum over lambdas. Because you want to go to the continuum limit, you trade off lambda with a smooth function rho of lambda. And once you go to the continuum limit, you say that this is the equation I'm now going to work with. Lambda are some parameters now in my theory. What I'm really interested in, how these lambdas are distributed. So rho is now the hero of your story, not lambda anymore. That's how you do
And the
this, right?
cut implies what?
So this integral, you see a cut here. The cut is because you see when you do this sum, you have to sum over j not equal to I, because you see you started from here where I was strictly less than j, and what you can do is you can write down 2 times sum over log lambda I minus lambda j I less than j as, without the factor of 2, I not equal to j, log of the same thing. Lambda 1, log of mod lambda 1 minus lambda 3 is same as log mod lambda 3 minus lambda 1.
Yes, yes.
So you basically take two of them together, that absorbs this factor of 2. But at no point, like I and j can be same because it will be singular. And here also you see that condition. So this condition of,
That just means principal value, right?
this just means principal value. That just means principal value. I'm going to actually, I mentioned here principal value of the integral. But yeah, it's in the next slide. Yes. Are there any more questions about? Okay. So this is the equation of motion at large n, and this is the cut integral. So curly C, always remember curly C is the finite sized interval over which my eigenvalues are distributed. So the cut in this equation of motion is the principal value of the integral. So what this means mathematically, so this is precisely what Akhil was asking. All this means is when you are trying to do this, actually define this integral. So suppose this eigenvalues are distributed over a range from minus a to plus a. So why minus a to plus a? Typically, all the potentials that we will consider will be nice potential. That is, they will be quadratic, quartic, sextic, and so on and so forth. So it will be some even power. Because you have even power, of course, m going to minus m is a symmetry. So your eigenvalues also follows this symmetry. So they are nicely symmetrically distributed around lambda equal to 0. That's why I have chosen minus a to plus a. Actually, you don't need to do that a priori. We will see that when we work out an example. It will turn out like the symmetries of your theory will tell you that minus a, it has to be distributed in that way. The point is, this principal value integral is defined as, so I know that when I'm trying to integrate this object, lambda prime equal to lambda is precisely when this object blows up. So I'm going to stop a little distance before lambda. More precisely, I'm going to stop a little distance before lambda by an amount eta. I'm going to skip this point eta. Then I'm going to continue defining my integral from lambda plus eta all the way up to a. So what I'm literally doing while evaluating this kind of a principal value integral is literally taking the problematic point and throwing it away. So this is how it is defined. And our goal is, given this kind of a potential W, we have to solve for rho of lambda. So remember, unlike other cases, we are now trying to solve an integral equation, not a differential equation. So once we get to this density rho of lambda, we can immediately start evaluating some extremely interesting quantities. Free energy, then there will be other correlators, objects like this, trace m to the power k. So the free energy, as you will see, so this is what Obinamada was asking. So this is what the continuum limit of S effective will look like. And now if you simply hit S effective with a variation, so variation with respect to rho has to vanish. So you immediately see you are going to take this del rho. So there will be an integral del lambda del rho. Here there will be some factor of half that will come because there are two rows. And that is precisely, again, you are going to take things out. Of course, you have to be a bit careful because lambda and lambda prime, like the two arguments on the two row are different. So, but it's a dummy variable. So because there are integral over both lambda and lambda prime. Here you will get a factor of half effectively, and you can also get to the equation of motion that way. So this will also give you this equation of motion. So you can also derive it directly from here. So one is, of course, as I was saying, one is the free energy, and the expectation value of general powers becomes simple moments with respect to this density functional. Now, the average in this planar limit, so what have we achieved? Notice that average of observables like this in the planar limit, because we are already in the 't Hooft limit, large n and such that t is constant. This is actually characterized by a classical density of states, because remember, we are right now doing saddle point approximation. So this is sort of like a classical solution. And this fact that planar approximation to QFT, that is diagrams, so we did not have any H cut or anything like that. We were looking at things that are planar versus non-planar. The fact that planar approximation to QFT can be regarded as a classical field configuration, this is something that actually goes back all the way to Witten's work in 80, and he was the first person who pointed this out. In fact, so after this, there had been many works on it, and I would also suggest everybody to look at this very nice chapter in Coleman's book. It's called 1 by n in aspects of symmetry. So there, I think Coleman has done a brilliant job of explaining Witten's work. Okay, now that we have discussed and we have obtained this large n equation of motion as an integral equation, we need to solve it. So in order to solve this, we introduce something new and novel. This is called a resolvent. So for finite n, this is how it is defined. It is defined as 1 by n trace 1 by z minus m. So m was the original matrix variable that we had. In terms of the eigenvalues, this simply boils down to sum over the inverses of z minus lambda I. If you take a naive n going to infinity limit, what you get is, again, an integral like this. Again, I have assumed that it is from minus a to plus a. Technically, you don't have to. This can be basically over the interval which I was calling curly c. So you see the interval here, curly c. Curly c is precisely the point where you have non-zero rho. Everywhere else, rho is 0. So another thing to note here is that we are now not anymore in real line or real plane. What we have done is we are treating this object z as a complex number, and we are going to leverage the machinery of complex analysis in a very significant way in what is about to come. So in essence, this object, like the motivation to define an object like this is the following. It is actually the generating functional of all possible correlation functions of this form. So you basically take all possible powers and you sum them up in this series. This is precisely what it is. Now, what we are going to exploit are certain properties of this resolvent. So always at the back of your mind, keep this to be, so this is our definition of resolvent. The first property is this resolvent that we just defined. This is analytic on the entire complex plane, except for that interval where rho is supported, the eigenvalue density. The eigenvalue densities, of course, lie, the eigenvalues lambda, they precisely lie on this interval, and the moment r, this function goes there, that is z hits those lambdas, you can see a singularity popping up. So it makes this integral singular. The very important thing is the asymptotics of this. Because of the normalization, as z goes to infinity, remember lambdas are all finite. What you can do is you can take z common out here. You can expand 1 minus lambda by z to the power minus 1 in a binomial series. And of course, the leading piece will simply be the integral of rho, which is normalized, which tells you that as z goes to infinity, the resolvent must have an asymptotic like 1 by z. It's very easy to check. It simply follows by taking z out common and doing a binomial expansion. The resolvent does something very interesting in the complex plane when it jumps across the branch cut C. So the branch cut C, of course, as we just discussed, it is not analytic over this interval. As this resolvent jumps across this branch cut, there is a discontinuity. And this discontinuity is precisely what we are after, this rho of lambda. The third property is that the potential that we started off with, this is related to the resolvent simply by its sum measured across this branch cut by sort of two representative elements across this branch cut. And both property 2 and property 3 can be explicitly proved by firstly noting that you have something like this, r of x plus I epsilon can be written like this. The first term that you see, this is nothing but the principal value integral. And you can kind of see why. This is what this integral does is it precisely takes you out of the problematic point when x is equal to lambda by adding this very small epsilon and then evaluating this integral. At the end of the day, you are going to take epsilon to 0. But once you evaluated it this way, what you will obtain are a very regulated answer. So you are literally throwing out the problematic point at x equal to lambda. The second piece, when you take the limit of epsilon going to 0, is precisely nothing but the Dirac delta function. So you are going to obtain a delta function of x minus lambda from here. Once you complete the integral over lambda, you're going to end up with simply a factor of pi. So pi is just a normalization that comes up in this representation of delta function. Finally, there is something in complex analysis called the Sokotski-Plemel theorem, which finally tells you that the resolvent across these branch cuts are related by this. So the moment you look at these relations, you can immediately see how rho and v prime, these two relations follow. By the way, this Sokotski-Plemel kind of theorem actually gets applied at a variety of places. In fact, one of the first places where we typically learn to use these kind of techniques is what is known as the Kramers-Kronig relation, where we are typically given the imaginary part or the real part of a Green's function in general condensed matter systems, and just by knowing either the real part, you can predict the imaginary part, and by knowing the imaginary part, you can predict the real part. So something very similar is also happening here. Here, all you need is data here. If you know r x minus I epsilon minus r x plus I epsilon, you can write v prime. Okay. So things were, of course, a bit restrictive, and we wrote down something which were true for one cut, and of course we also assume that our branch cuts are very nicely symmetric and so on and so forth, which will be good when particularly one is dealing with Gaussian as well as quartic matrix model. But due to Migdal all the way back in 83, we actually have a much more general solution. So, of course, a very important catch is that if we have a cubic potential, so if you have trace of m cube and so on and so forth, your distribution of eigenvalues need not be necessarily from minus a to plus a. It can be non-trivial. It need not be symmetric around 0. Now, given potential w of z, the most general expression that you can think of, as given by Migdal, you can determine of the resolvent is given by this. As a matter of fact, a priori you do not even need to assume anything about the eigenvalue distribution interval curly C. Let this be, but it has to be at least compact. So let this be distributed from A to B. What you can further show is now that the jump across the x-axis, if you have something very general like this, is given by this, the second line here. So this is nothing but the analog of this relation, this rho of lambda. So from the asymptotic condition, so using these relations, what you can see is from the asymptotic condition, so using this equation, all you have to do is take the z going to infinity limit, and you need to remember that in the z going to infinity limit, it always has to go as 1 by z. What you are going to get from the right hand side, curiously, will be some constant plus some constant by z. Now, the leading constant piece has to be 0. And this constant by z, this has to be 1. So, okay, there is a typo here. This is not going to be 0. This is going to be equal to 2t. actually. This is going to be 0. So as I was saying, that the leading piece coming from the right hand side will be some constant. And you see that from the asymptotics of R of z, there is no constant in front. And the first non-trivial term that appears at large z is 1 by z. And the coefficient of the first non-trivial term, when you equate it to 1, will give you the second equation here, which will be equal to 2t. Yeah, this is the correct equation. Yes. Okay. So having set up all these machinery, let us actually explicitly apply it for a particular model, namely the Gaussian matrix model. Now, we already know that for Gaussian matrix model, one can actually compute the matrix integrals exactly. There is absolutely no ambiguity about it. It's simply e to the power trace of m square integrated over all possible configurations of m. What we are going to test is whether our setup works in this case. So our potential is simply, sorry about the typo, it's just going to be trace of m square. Now, what we can do is, before assuming anything, let's just assume that our eigenvalues are distributed over some random interval from a to b. So in this diagram, the left end of this red colored line is a, the right end is b. And according to Migdal's prescription, in order to determine a and b, all I have to do is compute this closed loop contour integral where which goes around this cut C. So this red colored line is what is curly C. Of course, I have not drawn the explicit arrowheads, but this contour is going counterclockwise. One very easy way to do it is to deform this particular contour. And you can deform this contour by making this transformation z equal to 1 by p. Effectively, what this does is it sends this contour infinitely far away, except you are left with this point at this origin precisely because you have defined a transformation which picks up a pole. So now what you can show explicitly is the contribution of coming from the infinite points of this particular integrand is actually vanishing, and all you are left with is a simple integral around the origin in the p-plane. Once you do this transformation, at the end, you are going to end up with two integrals, integral 1 here and integral 2 here, from which you have to determine your a and b, which is precisely where the range over which your eigenvalues lie. The first equation will give you a plus b equal to 0, which is exactly what you expect. So you started off with a trace of m square piece, and you can see it very easily why that has to be the case. Because when we try to evaluate some kind of complex integral around the origin, what this is going to pick up are the residues. And as we know, residues simply pick up coefficients that are that basically gives you 1 by z. And once you expand out the object under the square root, you are going to see that the thing in the numerator is going to be precisely, once you expand out this entire integrand, you are going to get a plus b by z. The coefficient of the 1 by z term is a plus b, and that has to be 0, which precisely tells you that the eigenvalues has to be symmetrically distributed around the origin. The second contour integral fixes the value of a explicitly. Again, a very similar logic works here. Here, eventually you end up getting a to be 2 square root of t. And this, in fact, fixes the entire length of your interval over which your eigenvalues are distributed. In fact, this is quite expected, and this is something that you should be happy to see, precisely because it matches our usual intuition. From the discontinuity of the resolvent, what you can calculate is also the density in which your eigenvalues are distributed. And this object that you see here, square root of 40 minus lambda square, is precisely what is known as this very, very famous Wigner semicircle law, which is effectively the statement that if you give me random matrix theory, and in the large n limit, if I try to plot the distribution of its eigenvalues, it will follow more or less in the large n limit, it will become a semicircle. One can check this numerically also. Maybe that is something that I intend to show it in the next lecture, how to exactly numerically also get to the Wigner semicircle law, at least for unitary ensemble. And the reason why I mentioned that the spread of this interval from minus 2 root t to plus 2 root t should give you confidence in this method is because, as expected, as the 't Hooft coupling grows, as we were discussing, precisely this is what happens. The eigenvalues start pushing each other and they spread out more and more. Whereas when this t, the 't Hooft coupling, goes to 0, all of these eigenvalues start coming together, they bunch up at the minimum of the potentia, which in this case is m square, which is at the point 0 at the origin. And this entire interval disappears completely. So whatever we have calculated till now, including the distribution of the eigenvalues and the distribution of the interval and the length of the interval and so on and so forth, actually matches with all the intuition that we gathered till now. So in summary, what we saw was, at the very beginning, there was this ambiguity in diagonalizing Hermitian matrix model. We sort of extracted out this ambiguity, we calculated its volume, and we at the end demanded that things that I am going to calculate within the integral has to be independent of these so-called angular variables. We made this transformation and carefully computed the Jacobian in order to express our matrix integral. And this gave rise to what is known as the Vandermonde determinant. So in this process, we obtained a metric on the space of Hermitian matrices also. We looked at the large n limit. We discussed its equation of motion and its solution using a very particular method called the resolvent method. So there are other methods, by the way, also to solve equations of motion at large n. We looked at a particular example, which is the Gaussian matrix model, and we indeed got very nice results. We derived, we recovered the Wigner semicircle law, and we also we in fact also discussed the general case of when we do not have symmetrically distributed eigenvalues. So things like this can be used for cubic, quintic, and so on and so forth matrix models. So the next thing that I intend to discuss is, of course, we will notch things up in terms of complexity. Till now, we have only tested our thing for a simple Gaussian matrix model, trace m square. What exactly happens for quartic matrix model? How to deal with multi-cut solution. So here we assume that all the eigenvalues are divided on a single interval. So we had a picture like this. How if there was a red colored band here and another red colored band somewhere here and maybe another red colored band somewhere along the x-axis? What about multi-cuts? So there is no need that the eigenvalues always have to be within an interval like this. There can be gaps within the distribution. So these are called multi-cut solution, and exactly how one can study these. And of course, what I did promise at the beginning was the free energy, which I mentioned, can be computed, and the corresponding thermodynamics of such models. So how can we go to the free energy, and how, I mean, the free energy is in fact a very short computation from what we have right now. That is what is going to come up in the next lecture. And after that, we will move on to time-dependent matrix quantum mechanics. Yeah, so this is what I had for today, and I will be happy to answer any questions. Hello?
Yeah, please feel free to ask questions. I think today everything was crystal clear. Nobody has question. So
So what I will do is, of course, I will send these files to you. I think there are a few
few
typos here and there,
typos. Yeah.
yes, that I have to correct. Uh, Especially, I mean, this equation is wrong, and I also noticed this equation is wrong. So this 1 minus bz factor will not be there. Uh, I mean that you can see very easily once you plug one. I mean, once the first equation gives you a equal to minus b, uh, you plug it into the second equation, and yeah, you get 1 minus a square z square. That's kind of easy to see. So there are a couple of typos, and I will also send the list of references from where, which will be, I think, good for everybody to have a look.
Sure. Thanks a lot for the wonderful lecture. So see you next time.